Hello students. Welcome back to physics sessions. Today I would like to discuss the laws of motion, part 3. In previous parts we have discussed in part 1 and part 2 we have discussed about with the help of the free body diagram how to calculate the resultant force and acceleration of the system, and in the part 2 we have discussed about friction. So calculation of the required force in different situations when friction acts in that. So students, let us go to the concepts along with the tips and the tricks, and we are going to discuss the previous year's MCQs with the solutions. Students, you can download our Spark Academy app. There are daily live sessions, in-session doubt clarifications, free material in our app, tips and tricks. With the tips and the tricks, the concepts will be discussed and previous year's questions will be solved. So admissions are open for coming year. There is classroom and online coaching available. There are short-term and crash course and regular batches. So join us for the free live classes daily. Students, my sessions in a week will be on Tuesday and Thursday. Tuesday and Friday. My sessions in a week, physics on Tuesday and on Friday. Myself, Sandhya. Today I would like to discuss the laws of motion. So I will be helping you solve the concepts related to Eamcet, JEE and Neet numericals. Students, if you're buying any app from the Spark Academy app, use the coupon code SAN10, which is named after me. So by using this coupon code, you will be getting the discount on the course and you will be supporting me by using this code. Students, let us come to our session plan. So we are going to discuss friction, means we are going to continue the rest of topics from the question. What we have discussed already to calculate about the friction, when friction comes to play in the situation, how to calculate the required force, in different situations. So few of the situations we have discussed when friction plays in that situation. So let us finish the rest of the few more applications about that friction. And next one is constrained motion. So constrained motion is motion of the object by some force. That type of motion is constrained motion. So which type of questions can be asked in our competitive exams about the constrained motion and friction, how to calculate the force in different situations. So students, let us go to the topic. So here our concept is about the friction. So it is about friction Here we are given with the situation, motion of an insect in the rough bowl. Here you can observe in the diagram, here we are given with the hemispherical bowl, which is the rough surface. When it surface is rough, friction will comes to play in that situation. And there is an insect and crawling in that rough surface of the bowl. So you can see here at particular height, it reaches certain maximum height. You can see in the diagram. You can observe in the diagram clearly, the insect reaches maximum height with the support of limiting friction acting at this point. So it reaches this maximum height. So height is given as h. You can observe in the diagram. You can draw like this also. So this is the height. This and this height are equal. So when an insect reaches certain maximum height, here we have drawn the component of the forces acting on that object. So you can see here, weight will act downwards. So when an insect is at point A, weight of that insect acts downwards and perpendicular to the surface of contact. So here now the surface is like this. So here insect means weight acting downwards. This will reaction force or R. We can represent with N or R, normal reaction force. So towards the center of that bowl. And next, so to oppose this motion, when it reaching certain maximum height while crawling up on that surface, so to oppose that motion, it has the tendency to move down with this mg sin theta. So it can reach bottom of the bowl. So to oppose that motion, opposite to this component of force. See, you can see here, insect is here. You can imagine point is here. In this direction, mg sin theta, and opposite to that, limiting friction will act. Fl is the limiting friction. See, this is the free body diagram of this insect which is crawling in a rough bowl. In laws of motion concepts, which we deals with the effect of forces in different situations, free body diagram will help to find the required force in that situation. So this is the free body diagram of that insect when it is at a point A. So here weight is acting downward, and from and opposite to this will be mg cos theta because it is making angle theta. Here angle theta means here angle theta, alternating angles equal. And with mg sin theta component, it can reach the bottom of the bowl. So to oppose that, maximum limiting friction develops as the surface is rough. So these are the components of the forces. So now let us see what is the height reached by that insect in the rough bowl. So we have to find here height reached by the insect in bowl. So that is our question. So at point A, so whenever we are finding the required force, we consider the object or a block, or here object means here motion, we are talking about the insect. That insect is at equilibrium condition. So for the condition of equilibrium, for condition of the equilibrium means all forces will be balanced, then sum of the forces acting at that point will be equal to 0. That is the condition of equilibrium. So for the condition of equilibrium at the point A, So what are the balanced forces we write? See, reaction force is balanced by the mg cos theta, and limiting friction value is balanced by the mg sin theta. Now, take this is equation 1 and equation 2. Divide equation 2 by equation 1. So what we get sin theta by cos theta, that we get it as tan theta, which will be equal to F limiting friction by R. And we have known that since maximum limiting friction value will be equal to mu into R. So it can be written as like, from this we can write, we can substitute FL value as mu R. So it is equal to tan theta is equal to mu by mu. That's all. Mu R gets cancelled. Remaining is mu. And from this figure, so A, O, and give it is like point B. So let me give you here, it is point B. So from AOB, you can see here from AOB triangle, mu is equal to, find the mu value. Means tan theta value, as it is y and it is radius of that, which will be equal to radius of that hemisphere. We can take it as like R. So mu can be written as, which is the tan theta, will be equal to under root of, means opposite by adjacent actually. So it is R, it is y. In the figure, this opposite side will be under root of R square minus y square. So it can be written as R square minus y square by y. That is from the figure. Or you can write, or y is equal to, write in terms of y. So it will be equal to, means separate the y value, square on both sides, root gets cancelled. So remaining will be equal to R by under root of 1 plus mu square. So tan theta is being equal to mu, and from the figure tan theta is being equal to under root of R square minus y square by y. And we have written that in terms of y, that is y is equal to R by under root of 1 plus mu square. Here we need to find height reached by the insect in bowl. So for that, this height we need to find what is this h value. This total is R and minus y. So from figure, we can write h is equal to R minus y. And y is this much. So substitute that value here and take common R. We get R into 1 minus 1 by under root of 1 plus mu square. So this is the height reached by the insect in a rough bowl when maximum limiting friction develops at that point. So they can ask these type of applications. So they can ask to calculate the height, or if they're asking what is the maximum limiting friction develops. So to find it, you can use mg sin theta when they given angle. So this is the situation. Next situation is minimum mass hung from the string to just start the motion. See, look at the diagram. So what should be the minimum mass hung from the string? This is the hanged mass, M2. What should be this mass to start the motion of this system? So how much mass need to be hanged here? That is the situation. So let us find that. Let us observe the free body diagram of this system first. So if we look at the block M1, first block of mass M1, here tension will act towards the string, its weight will act downwards, opposite to this will be reaction force. And here, M1 is placed on rough horizontal plane and M2 is hanged. Now we need to find what should be this mass hung from the string, then it can start the motion. So here in this M2, what are the forces acting? There is a tension which creates by this weight of this M2, that is M2G, which is acting downward, creates the tension along the string. So these, as it is a rough horizontal surface, so to oppose this motion, block M1 has the tendency to move in this direction. So for that required mass, when it starts the motion, it has the motion downward. So to oppose this, opposite to that limiting friction, maximum limiting friction develops. So this is the free body diagram of this system. Just we have visualized forces acting on that object. Now let us see. So we need to find what is that minimum mass hung from the string. So for that, we can take here tension will be equal to, at this situation, tension is nothing but for equilibrium condition. EQM means equilibrium condition. T is equal to the tensional force along the string balanced by the maximum limiting friction develops. And this T is created due to this mass M2. So we can write M2G is equal to F into, means limiting friction value. I can write it as like mu R, since maximum static friction or limiting friction value is equal to mu into reaction force. And we can say, so for equilibrium condition, T is equal to Fl and reaction force is equal to M2G. Sorry, M1G. Reaction force is balanced by weight of the mass M1. Now we can substitute R value as M1. So this implies M2G is equal to mu into M1G. Then both sides G cancel. So we can find M2 is equal to mu M1. So this much force, this much minimum force should hang from the string, then it can start the motion. So just from the free body diagram, balance the forces for equilibrium condition and find the required one. That is the concept here. Next situation, when a mass M1 is placed on a rough inclined plane. See, here also we need to find what is the minimum mass should hang from the string, then it can start the motion. That is the situation. But here, one object is placed on rough inclined plane In previous situation, it is placed on rough horizontal surface. Here it is on rough inclined plane. M2 is hanged. So what should be this minimum mass to start the motion? So just to look at the figure, free body diagram of this system, which is given with the forces acting on that object. So here weight of the object will act downwards. Here angle will be theta and it will be m1g cos theta, and opposite will be m1g sin theta. So the m1 block has the tendency to slide on the inclined plane, to slide down with this component of force. But we are finding minimum mass should hang, then system can start the motion this direction. So we need to take direction of m1 up the plane. So to oppose this motion, limiting friction also develops along m1g sin theta. So the total force on inclined plane downward is m1g sin theta plus Fl, which is the limiting friction. And this m1g cos theta balanced by the reaction force, because reaction force always acts perpendicular to surface of contact. And for m2, we can observe here weight of m2 will act downwards, that creates the tension along the string. So towards the string, the tension will act. So here, for equilibrium condition, for the condition of equilibrium, just write the forces acting. First we take for m2, T is balanced by m2g. Take it as equation 1. And next for m1, T is equal to, this tension is balanced with m1g sin theta plus limiting friction value. Take it as equation 2. Since we can write this second equation like this also, T is equal to m1g sin theta plus, we know that F is equal to limiting friction develops at that situation is equal to mu into R. Here R is balanced by m1g cos theta, so we can write mu m1g cos theta. Since R is equal to m1g cos theta. So now take this one as equation 2. And now from 1 and 2, consider the equations 1 and 2. Substitute T value as m2g. So m2g is equal to m1g sin theta plus mu m1g cos theta. From both sides, G cancel. So the minimum force should hang with the string to start the motion is m1 into, you just take common m1 from the right hand side, and 1 into sin theta plus mu cos theta. So this is the minimum force should hang with the string to start the motion. So we just considered the condition of equilibrium and we balanced the forces and we are finding the required quantity. Next situation, sticking of a block with accelerated cord. See, in in this diagram, you can observe there is a cart which is accelerating in this direction, in rightward, and the block is kept in front of on the face of the cart. So what should here the question they can ask? Minimum acceleration, a minimum of cart, so that the block does not fall. The block does not fall. So what is that minimum acceleration should maintain by the cart? Then the block on front side of the cart will be in a static position, means will be at the rest position. Means it does not fall. That we need to find. So you can observe here, so we are describing the motion of the block with respect to the cart, but cart is accelerating. Now the cart is non-inertial frame. It is non-inertial. It is non-inertial frame. So in non-inertial frames means directly Newton's laws are not applicable. Pseudo forces will act. So you can observe free body diagram of that block. So with the effect of this acceleration on block M, pseudo force will act. Pseudo force is the imaginary, means which is not virtual force, which acts in opposite direction. Equal in magnitude but act in opposite direction. You can see the free body diagram of that block M. Weight will act downwards, so it has the tendency to move down with its weight. To oppose that, maximum limiting friction develops. Now, as it is in contact with the surface of the cart, reaction force will be in this direction. So with respect to the cart, pseudo force will act opposite to the real acceleration. So this is the acceleration with corresponding force, this force. So now in this direction, pseudo force will act, which is equal to MA. Pseudo force has the same magnitude of external force, but will act in opposite direction. So this is limiting friction. So just we have drawn the free body diagram of the block. Now we are going to calculate the minimum acceleration of the cart, so the block does not fall. Students, what can you think here? We must take a condition of equilibrium of the block. Means if sum of forces acting at that point on the block equal to 0, it will be at rest. So for the condition of the equilibrium, we can see here limiting friction, whatever maximum limiting friction develops, it should be greater or equal to weight of the block. Then only it can be at rest. When the cart is accelerating, the condition for the equilibrium state of the block, which is on the face of the cart, the maximum frictional force develops should be balanced by its weight, or it can be greater, but it should not be less. If it is less, the block has the tendency to move down. And we know that FL is equal to mu R. And R is being equal to in the situation, in this free body diagram, for equilibrium condition, R is balanced with pseudo force acting on the block. So we can write M into A. So we can use this FL value and R value. We can write here mu into MA, which should be greater than G. Then mass, we are talking about the motion of the block, not to fall from the surface. What is the condition we are checking? So now, so the acceleration of the cart should be greater. The minimum acceleration is G by mu. So now you can say this is the condition, then the block does not fall from the surface. That is the minimum acceleration. Or they can ask, what is the minimum force required? Minimum force required for the system means this force to accelerate the cart, that is the total mass into that minimum acceleration. So you can write here the minimum acceleration m plus m into G by mu. So this is the situation. That is the minimum force and this should be the minimum acceleration. And next situation is maximum length of the hung chain. So we can see here total length of, let us consider L is equal to total length of the chain and in that L dash length is hang, L minus L dash is remaining length. Now L minus L dash is placed on the horizontal surface. Now they are asking what should be the maximum length of the hung chain, then it has a tendency to move down by the weight of M2. So to oppose that, in this direction, limiting friction acts. So the condition here not to fall off from the horizontal. Now, what should be the condition? This frictional force must be balanced by the hang weight. So you can write for the condition of equilibrium, for the condition of equilibrium means to be at rest, not to fall from the horizontal, is limiting friction should balance it by hanged weight. Hanged mass is M2, its weight is M2G. And maximum limiting friction develops is mu R, that is equal to M2G. Now, R is reaction force is balanced by the weight of the mass on the horizontal surface. That is mu into R is balanced by M1G, which is equal to M2G. So G cancel, then coefficient of friction is being equal to M2 by M1. As mass is proportional to length, from this equation we can write mu is equal to hanged length. M2 is the mass of the hanged portion. So hanged portion length is L dash by M1 is the mass of the remaining length on the horizontal. So the remaining length is L minus L dash. So from this, next we can write, means we need to find what is the maximum length of the hung chain. So hung chain length is equal to L dash, that is hanged portion. So from this equation, L dash will be equal to, separate the L dash value. Actually, before this, we will be having the step 1 by mu will be equal to L by L dash minus 1. So from this, L dash will be equal to mu into L by mu plus 1. This much length should hang not to fall from the horizontal surface. From the total length, this much length should be hung from the table for the static position, for the rest position. Now this is the hung chain length. Now if they're asking in the same situation, what is the fractional length hung from the table? Fractional length means we need to, which is hung from the table. So we can write L dash by L. So from this equation only, L dash by L will be equal to mu by mu plus 1. So if they ask what is the fractional length hung from the table, fractional means you need to take the ratio that hung length by total length, that is the fractional length. And what is the fractional length? Fractional length that remain on horizontal surface. Means here fractional length hung means that hung length by total length. Fractional length that remain on horizontal means we need to find, or let me write for this point, that is L minus L dash, this is the remaining length, by total length, which will be equal to 1 by mu plus 1. Because L dash is mu, L is mu plus 1. So L minus L dash by L will be equal to 1 by mu plus 1. So when some portion of chain hung from the horizontal surface of table, they can ask what should be that hung chain length. They can ask to calculate this L dash, and they can ask what is the fractional length hung from the table, or what is the fractional length that remain on the horizontal surface. These ways they can ask the questions. Students, this is so this is by mistaken. Actually, we have already discussed this concept in previous parts of NLM, laws of motion. So it is cancelled here. The only situation, the only concept is what should be the maximum length of the hung chain. So see, every situation, students, you can understand at every situation to calculate the required force, we are taking equilibrium condition from the free body diagram of that situation. So free body diagram, you must understand how to visualize the forces acting on that object at that particular situation. Then we can calculate the required force. Next, about the next concept is constrained motion. Constrained motion means motion of one body is dependent on the other body. That type of motion is constrained motion, or you can say if motion of one object is restricted by the other is also called constrained motion. So we need to give the relations, constrained relations. So for that first, the relationship of displacements, velocities and accelerations of the two bodies are called constrained relations. So how to give constrained relations we discuss with the different situations. You can see here case 1, we are given with the pulley string system. So to give the constrained relations, mainly 2 points we need to remember. First point, find distance of the objects in that system. Distance, how many objects present. You need to find the distance of the objects from fixed points. From fixed points. Next, use the condition. What condition we have to use? Length of the string remains constant. Length of the string remain constant. So to give the constrained relations of any system which are being controlled by the motion of one body with respect to other, we need to find distance of the objects first from the fixed points, and we have to use the condition length of the string remains constant. So let us deal with this situation, pulley string system. So in this situation, so first what we have to do, distance of the objects. And you can see there is an applied force on the pulley. And we did not give any mass here, so it is a massless pulley, consider. Now, one is pulley, it is at what distance from the support? This is the fixed position. So you can take, it is at x distance and the block is at what distance? From here, from the pulley. So by the application of the force on pulley, the system will move together. Means one body is dependent on the other body. So let me say what will be this distance from this fixed point. This distance will be, actually this total is x, until here it is x. Now the block distance from the pulley, we can take it as x minus x. So just we have given distance of the objects from the fixed points and use the condition length of the string remains constant. So by using the condition, that is x plus x minus x remains constant. And we can give the constraint relations. After displacements given, differentiate that with respect to x. So we are doing here differentiate with respect to time. We get displacement is differentiate with respect to time gives velocity relation. So we can write, actually this equation becomes 2x minus x, which is a small x, is remains constant. So now differentiate with respect to x means it will become 2 into, so one is a pulley, one is the block here. The pulley from the fixed point, it is at a distance x, and the block from the pulley is at a distance x minus x. So we are differentiating dx by dt minus dx by dt will be equal to 0. So where x is the distance of the pulley from the fixed support, so which gives velocity of the pulley minus small x is distance of the block from this fixed support. So now it will be the velocity of the block will be equal to 0. So from this we can write 2 times of velocity of pulley is equal to velocity of the block. So here, one time if a block moves the same length 2 times, the pulley moves around the string is around the pulley. It moves in this direction x and in this direction x 2 times. So this way, by considering the displacements from fixed points and can give velocity relations and can give next, if you differentiate this velocity, what we can get 2 times of acceleration of the pulley is equal to acceleration of the block. So these are the constraint relations. So in any situation, and this is the displacement relation. In any situation, to give the constraint relations, first we need to find the distance of the objects from the fixed points. And we need to use the condition length of the string remains constant. Differentiating distance with respect to time gives velocity. Differentiating velocity with respect to time gives acceleration. So what they're asking? If they're asking velocity of the pulley or velocity of the block, we can use this relation. If they're asking what is the acceleration of the pulley or acceleration of the block, we can use this result. So let us go to next situation. Here we are given with the pulley string system only. We can observe here. There are 2 blocks. One is on horizontal surface, one is hanged with the string. That string is passes over the pulley. So from the pulley, second block is at what distance? Y distance. And from the fixed point, this is the height h. So from the pulley to ground, it is h. And block 1 is from this position, it is at a distance x. So from here, it traveled this much distance. And this is being hypotenuse. So first we need to relate the displacement equation. So from the figure here, under root of means length of the string, we need to use the condition. Already in the figure, the distances of that object from the fixed points are given. See, block 2 is at y distance. Block 1 is at under root of h square plus x square distance. So in this system, it is already given with the fixed distances from the fixed position. Now, we need to use the condition length remains length of the string. Length of the string, this side it is under root of h square plus x square and this side it is y. Remains constant. So here we have used the condition on differentiating with respect to time. So we need to find what is the velocity of this block, with which velocity it moves, that block 1. So here we are going to differentiate the above distance equation with respect to the time. So take equation is under root of h square plus x square plus y is equal to constant. So by differentiating, treat this as like root x will be 1 by 2 root x means 1 by 2 root x means under root of h square plus x square. Differentiation of root x is 1 by 2 root x. And again, x term need to differentiate, so into 2x will come. Plus, means 2x into dx by dt. Now the differentiation is finished. Next, it is minus dy by dt is equal to 0. Why it is minus? Actually, here we get, while differentiating this term, here we get minus. By taking common, it will become minus dy by dt equal to 0. So the direct step I given. So the differentiation of this, we get minus 2x by 2 into under root of h square plus x square plus dy by dt. By taking common minus, the second term becomes minus. So now 2 cancel. And next, so here we need to give the with which velocity they move, velocity relation we need to give here. So this implies from the figure 1 by under root of h square plus x square is means x by under root of h square plus x square is cos theta into it is dx by dt is the velocity of the first block v1 minus dy by dt is v2 will be equal to 0. So v1 will be equal to v2 by cos theta. This is the relation. So here we are finding velocity of the first block, or you can find velocity of the second block. So first we related distances, means we measured distances from the fixed position, and we used length remains constant. By differentiating, we got here velocity. And one more important case about the constrained motion, that is wedge block system. Let us see one situation. Here we are given with a wedge which is accelerating left side, and the block is placed on the wedge, and this angle of inclination is theta. Now the wedge can travel this distance. So now question is, for what value of A, which is the A means acceleration of the block, the block falls freely from the wedge. So what is that acceleration we have to find? So first let us consider the distance traveled by the wedge with an acceleration. Initially it is at rest. If it moves this much distance left side, we can write it as x is equal to half at square from the kinematic equations. And so take it as this is the height of the wedge, then the block falls freely from this height. Then it is equal to, then the block falls freely due to gravity. When the wedge accelerates left side, then it falls freely due to gravity, that is h is equal to half gt square. Now we need to find what is the value of that A, which is the acceleration of the acceleration of the wedge for the block falls freely. So from above two equations x and h, divide them. X by h gives you half t square will be cancelled. it is equal to A by G. Then this implies XYH is nothing but means adjacent by opposite side is cot theta is equal to A by G. Then A is equal to G cot theta. So this much is the acceleration of the block, then acceleration of the wedge. This is acceleration of wedge, then the block falls freely. So this way we can solve the questions about the wedge block system. Students, you can download the app for the great discounts. In app, free handwritten notes and study materials, previous year's questions and free mock tests. And if you're buying any course, for the admissions, you can contact any of these numbers displayed here. And don't forget to enter a coupon code SAN10. By using this, you will be getting the discount on the course. There are daily and on-demand live sessions. So our methodology is from the basic concept, shortcut methods, all model questions, exercise questions, previous year's questions, chapter-wise tests, weekend tests, grand tests, and test analysis will be done. Students, let us see the previous year's model questions related to today's session concepts. The first question, it is like a constrained motion. But we can easily solve what they're asking required quantity. In the given figure, the pulley is massless and frictionless. There is no friction between the body and the floor. The acceleration produced in the body when it is displaced through a certain distance with the force P will be. So here, now P is the force acting on that massless pulley. This creates the tension along the string. So towards the pulley, the tension will act along the string towards the pulley. Now, this pulling force is balanced by 2T. So towards pulley, how much tension acts? This T plus T, 2T. And pulling, that applied force gives the acceleration in that block. We can write it as MA, means which is given M. So we can substitute P value here. It gives MA is equal to 2T. So from that, acceleration of the block will be equal to 2T by we are talking about the block here. So yes, at the block, at this situation, the block is MA is equal to, only force acting on the block is tension. So the resultant force on block is tension. So MA is equal to T. And now we can write A is equal to T by M. But T is equal to P by 2. From here we can see T is equal to P by 2. So acceleration of the block is P by 2m. So just they're asking acceleration produced in the body only. So what is the applied force balanced? The applied force is P here. P is balanced with 2T, which is acting towards the pulley. And we are talking about the acceleration of the body of mass m. So in this free body diagram, the only force acting on that is T. So M into A will be equal to T. And from this pulling force, we have taken T is equal to P by 2. So this will be the acceleration of the block. Next, a block is kept on frictionless inclined surface with an angle of inclination alpha. Incline is given an acceleration A to keep the block rest, means stationary. Then A is equal to. So what should be that acceleration? So this way, the incline is accelerating. Now on the block, opposite to that, means at this block, first draw the component of forces. Weight will act, and it can move. It has the tendency to move down. But with respect to the incline, so opposite to this, pseudo forces will act on the block, that is MA, which is opposite direction of the real acceleration. And now it is making angle theta with the incline. So this pseudo force resolve into components MA cos theta. Now for the incline is given an acceleration A to keep the block stationary. So these are the forces acting on the block to move on the incline. If these two forces balanced, then it will be at rest. So we can write MA cos theta should be balanced by mg sin theta. So from this, we are writing forces acting on the block due to acceleration of the incline. Actually, alpha is given, but I consider theta. No problem. It is inclination is alpha. So we can write alpha everywhere. So A is equal to both sides m cancel g into sin alpha by cos alpha, which is equal to g into tan alpha. So this should be the acceleration. So students, this is the required discussion today. So related to concepts, very few questions are discussed here. Thank you. We meet in the next session.